Hi everyone, my name is Avraham. I'm representing Polaris Research, and today I'll be speaking about a short workshop paper we did called Exploring Asynchronism in Swarm Parallelism. The authors are the employees of the company, Jan, myself, AJ, Samir, and Alex. So here's the outline of what I'll be talking about. First, I'll be talking about asynchronous training in distributed networks. And then asynchronous pipeline parallel, for those who don't know the background of that. I'll revisit swarm parallelism, and then I'll talk about Nestor of accelerated gradient for delay correction, and finally some experiments. Just a brief high level. So the gist of this talk, it was a two-paper workshop, and what we mainly explored is how to perform asynchronous updates in local nodes. And the change was actually very simple. It was to change the optimizer from AtomW to a Nestor-based optimizer. And I guess for those who sort of understood what I just said, that's the gist of it. It's actually quite simple. But for those who don't know pipeline parallel and async works in pipeline parallel or swarm at all, this talk will cover all of that. So first of all, why is asynchronous training in distributed networks important? Distributed training infrastructure is quite heterogeneous. That means you have different compute speeds, different GPUs, different bandwidth connections. All this causes, like, you can have stagger effects. Things can become quite slow. It takes time to sync stuff, and generally it can be quite messy. The current dominating paradigm is synchronous type training. In synchronous type training, you have a lot of nice convergence guarantees when you train stuff synchronously. You have good proofs with SGD. But the problem is when the model gets quite big, you need to start splitting your models across different stages. So you have each layer going on a different stage. I'll be talking about that. That's pipeline parallel. And then you get stuff like synchronous bubbles. Asynchronous training is appealing because it alleviates a lot of these issues. So things can work asynchronously. You don't have to wait for stuff to sync. But it has a fair amount of challenging. Some of the challenges we'll talk about here are going to be stale gradients and outdated weights. Those are two dominating problems with these kind of works. So first of all, pipeline parallel, for those who are less familiar with it, if you have a very large model, you want to split that model onto multiple stages, up to multiple GPUs. You take how many ever layers that fit onto a single GPU in your kind of cluster, and then you put those layers on them. The method was initially designed for synchronous type training because of the convergence guarantees I mentioned. So the way it kind of works is pretty simple. You have a single batch. It gets processed by the first stage, and then it gets passed on. And while this is happening, this GPU will remain idle. So that's not very good. Various methods have been coming up over the years to improve the utility and reduce the idle time between the different layers. So the first one was G-pipe, which came with the approach of splitting up to micro batches. So now you have a batch and it's split up into micro batches, and normally you put the micro batch to be some multiplication of the number of stages that you have. These have what we call these sync bubbles, and over the years, various methods like 1F1B, an interlived 1F1B, and zero bubble came through to try to reduce this kind of bubble time. So the kind of less known methods in this area are asynchronous pipeline parallel. The promise of this kind of approaches is that there's no synchronous bubbles. So once, let's say once you have the startup state where you have your first initial micro batches that go through, from there on, each node performs the update of its gradients immediately once it sees the batch. So different challenges occur in this kind of work, in this kind of method. You have outdated gradients, you have outdated weights, and so the two main methods that are known here are called pipe dream and pipe mare. And the next few slides, I'll be doing a bit of notation and formulation, so we can all speak the same language. So let's formally talk about it. You have a model that's split into P pipeline stages. Each function f is a function in your stage, so a composition of that gives you the final model. For an input x, all the weights are w. Similar for the backwards, every g is basically dy to dx, so the derivative of the model stage. And the error input at the stage P is basically your loss. So for the synchronized pipeline parallel, the definition is the error computed at stage I minus 1 is basically your Becker gradients of the weights at that stage. There's a notation T here. For the synchronous case, it's not that important, but we'll see when it's async, this T does have importance. And you have your error signal. And H is the chain rule for the layer I at time T. And this is how you're computing your derivative at the stage of stage I. And so the update is SGD, which we all know. And for the synchronous case, it's pretty much equivalent to the regular training we all will kind of know without a pipeline parallel. So what happens with the async pipeline parallel? What happens to these equations? So first of all, the forward pass is updating the weights, is performing the forward pass at some time t minus tau, because the activation is going from stage I all the way to the last stage and then coming back. And by the time it comes back, because you're performing local updates, those weights have moved on. So in this case, you have a staleness of the gradients, and thus the error that will be computed will also be stale. And then similar for the chain rule, those weights have been updated, though the gradient at the moment it comes to those weights, it's going to be delayed by tau, which is corresponding to the stage and the number of stages. And finally, the whole gradient they're going to be computing and updating your weights with is delayed and using incorrect error signal. So one of the methods that tries to address this is what we call pipe dream. This is the name of the paper, and what it does, it uses weight stashing. So the idea with weight stashing, every time you compute a forward pass, you stash those weights, and later when you encounter the same activations that come back now in the gradient, you pop out those weights. And so at least the error signal that's computed is computed with correct weights. The update equation is still using old weights because you're popping the old weights for computing the chain rule, but it's better than computing it with the new weights and an outdated error signal. So this is the notation for pipe dream. And these equations are recalling the issue we had when I defined the synchronous pipeline parallel. These are the same equations here and here. And the work called pipe mare actually doesn't do weight stashing. it handles the forward-backward weight discrepancy by using a stage-wise learning rate. So the kind of intuition they have is that earlier stages, they experience more gradient distortion, and so the learning rate is inversely set to the delay. So the earlier stages effectively have a lower learning rate, and thus they have less distortion when they're outdated. For those who don't know swarm parallelism, I'll do a quick revisit because the majority of our work was doing tests on this. So swarm is a two-dimensional pipeline parallel work. It does stochastic routing. It has improved GPU utilization, and it supports fault tolerance and node elasticity. It aims to be close to synchronized training dynamics. What it does is that every node in the stage accumulates gradients, and once there's a target batch size that's hit, all reduce is performed. One of the issues with swarm is that the kind of sync bubbles become more dominant once you have more nodes in the stage and you have more stages. And so one of the things we explored in this work is performing local updates in each node. In that case, you don't have to accumulate gradients and sync those once you hit your target batch size. So a quick recap on accelerated gradients. These are equations. I think most of you know this. This is quite a well-known work. The velocity term is used to perform a look ahead and thus provide you a more stable convergence by stabilizing the training. And then recall in our case, the main intuition for us changing the optimizer from AtomW to optimizer that uses Nestor style updates is that now we use the velocity term to perform weight correction. So if the weights are delayed because they were computed using old gradients, now you perform, using the velocity, perform weight correction, and thus you alleviate some of the issues that occur due to synchronous training. These are the experimental setups. We use 8 stages, and we have 2 nodes per each stage, which is quite small. And to emulate the delays, we add delay computation, so it's 1 second, 0.5 seconds. And so here's inspecting the training stability. So what we do is half the warm-up time from 1K to 500 steps to see what happens. And for our case, it's what we call the async NADM, batch size 64. And this is quite more stable than the other baselines, which use the vanilla AtomW. We explore what happens when we use different batch sizes. In this case, again, when you have the vanilla async without our optimizer, it does not converge. And lastly, when we introduce more staleness by randomizing the delays, again, you can see the vanilla case of batch size 64 does not converge at all, and for our cases, it does.
Thanks for the talk. I was wondering if you know the impact of latency on the pipelining stage, and so how the async is helping with the latency.
So, yeah, when you have asynchronous style updates, you actually mask out the latency because you don't have to wait for the synchronous style to happen. So that's one of the benefits.